So what's the last theorem that we want to look at? It's called Stokes' theorem. Stokes' theorem is really a generalization of Green's theorem. What does it say? Here it is in all its beauty. Let S be a piecewise smooth orientable surface. Okay, so its edges could be triangles. It could be a tetrahedron kind of shape. I think one of the problems we'll work through, maybe we should work through it first, is number 11. It is a tetrahedron kind of shape. That solid is a tetrahedron. It's got four sides: this front triangle, the back right triangle, the back left triangle, and the bottom triangle. The surface is piecewise smooth. The pieces are the four sides, and they are planes, and so therefore they're smooth. Is it an orientable surface? The reason it is orientable is because you can create a consistent outward pointing normal vector. You got a normal vector coming straight out of the page at you, is consistent with outward pointing normal vectors pointing straight to the right over here, straight into the page over here, and downward on the bottom side. If you can consistently define a normal vector outward pointing like that, that's effectively the definition of orientable. Boundary is a piecewise smooth curve. Yes, all these triangles are made up of straight lines. Straight lines are smooth. And there's pieces. There's how many of them? 1, 2, 3, 4, 5, 6 of them. Let C be traversed with respect to n according to the right-hand rule. And let the components of f be nice, continuous first partial derivatives. Okay, we actually, in this problem number 11, are not going to focus on the entire three-dimensional solid. Stokes' theorem, you focus on, say, one of the surfaces, one of the triangles. So you might say it's a little easier that way. You don't have to focus on all the faces. That's not a flux line integral. That's a circulation line integral. Line integral around the closed surface, which again in number 11 will be a triangle. Measuring the circulation around the triangle. Notice it's f dot dr. It's not f dot nds. This is the kind of integrand that we had earlier with Green's theorem, f dot dr. Is really, when you get down to it, f dot the unit tangent vector, ds actually. If you're forgetting that, let's look back earlier in the chapter. Notice right there, f dot er is f dot t ds. Effectively, you're dotting the vector field, that you got this curve. You're dotting the vector field, which is kind of in the background, with unit tangents to the curve. Effectively finding components of the background vector field that are tangent to the curve, that are flowing with the curve, so to speak. And so when it's a closed curve, that's why you call the line integral a circulation. It's somehow measuring overall how much the vector field is circulating with the curve in question. That is what's going on here in Stokes' theorem. F dot dr. So this is a circulation. Is the double integral over the surface of, that's really more like a surface integral, the curl dot n. So if you had to try to draw a generic picture here, you've got some surface sitting inside three-dimensional space. Imagine this is a three-dimensional picture. This is not a curve in the plane here. This is a curve that's on a surface inside three-dimensional space. You orient the curve with respect to a certain orientation based on outward pointing normal vectors. Well, they don't, it's not a closed solid, so they're not necessarily thought of as outward pointing. But you pick some direction for your normal vectors. Maybe you point upward. These are your normal vectors. The curve, the outside curve, C, is going to be oriented with respect to those outward pointing normal vectors, okay, here we go, right-hand rule, but don't write on your right hand as in gen physics. People were talking about that before class, that you could write on your right hand for your gen physics exam, but you should wash your hand before coming here on Monday. As you go around this curve with your fingers following the curve in the orientation indicated, your thumb should point in the direction of the normal vectors. If this were a planar picture, you would call C going around this counterclockwise. And the normal vectors would be pointing straight up out of the page. And Green's theorem would apply to that. Again, Stokes' theorem is a generalization of Green's theorem. But again, there's a background vector field. You know, what do those vectors in the vector field look like? Who knows? They could be doing lots of weird things. Some pointing up, some pointing down. And they're three-dimensional vectors. They're in space. That's your background vector field. You're finding the curl of that vector field, which is a new vector field. Dare I draw it? No, I don't think so. With this random drawing of these red arrows, I really have no idea what the curl vector field would look like. But you could compute it. It's a three-dimensional curl. You either have to compute a determinant or use the trick for computing cross products way back when, right? Where you add more columns and you go down these columns and down these rows and do some additions and subtractions, or have the computer do it. Or in the final exam, maybe I would just give it to you so you don't make a mistake, right? I did talk about this with people before class as well. Like, I'm trying to make the final exam doable and gradable in a reasonable amount of time. And so I have to do things to try to help you. So you actually can maybe even get right answers in 15 minutes or something to a problem. And you don't make mistakes, hopefully, and I can grade it more easily. So you focus on concepts on the final exam rather than doing these 1.5 hour long problems where you're guaranteed to make a mistake somewhere. And that mistake could lead to other mistakes, and it's just a nightmare to grade as well. So again, you can create a new vector field, the curl. You know, F is going to be maybe M, N, Q. The curl is going to be a vector of partial derivatives. Py minus nz. Oops, that's not a Q, it's a P. MNP. Py minus nz, comma, mz minus px, comma, nx minus my. It's another vector field. Yes, I dare not draw it. But again, Stokes' theorem says in this kind of situation, and assuming F is nice enough, that the circulation of F around this curve can be found by doing a surface integral of the curl dot n with respect to an area element over this surface that's C bounds. Surface is this thing here. Usually a different color. This is the surface. So that's what Stokes' theorem says. Let's try to confirm it with number 11. You know, this book does things at the level of confirmation. Can we do the calculations? Can we see that we get the same thing? We don't even come close to doing proofs. But I would like to, maybe a little bit today and a little bit on Friday, try to get a little intuition. But at the moment, we're just trying to see that we can get the right answer. So number 11, so once again, this picture. What do the directions say? Looking up here, it says in 9 through 12, C is the boundary of a surface giving along a vector field. Verify Stokes' theorem on C to show this works. Here in the directions for number 11, C is the curve that follows the triangle that's the closest part of the solid to you. Actually, you can just think about the triangle. You don't have to imagine a solid like you did in the assignment for today. You can just think about this triangle as being the surface you're focused on. going from 0, 0, 2, that's this one, to 4, 0, 0, to 0, 3, 0, and back to 0, 0, 2, in that order. They don't tell you what the outward pointing normal is. So, well, okay, but they do tell you what the direction of the curve is. So the arrows that you could draw here, when starting to show some work by hand, they describe the orientation of the curve. 4 right there for X, 2 right here for Z, 3 for Y. They say go around the curve in this way. So you could draw arrows like that. That would mean, if you think about the right-hand rule here, the normal vectors would be outward pointing. Pretend this arrow is coming towards you. That would be the end. And that will affect how you do the surface in it to verify Stokes' theorem. All right, so how would we actually verify Stokes' theorem? As far as the line integral goes around the curve, you got to do it in 3 pieces because it's a 3-piece curve. An R1, an R2, and an R3. That would be functions of t. This is a curve, not a surface. Maybe we want to use letters to represent the points. P is 0, 0, 2, 0, 0, 2, yep. Q is 4, 0, 0. R is 0, 3, 0. R1 goes from P to Q. There's P, here's Q, here's R. So a quick way to do this, to parameterize this, is effectively to start at P like this and add T times Q minus P. That's a quick way to parameterize it. There's the formula. You do need to keep track. When you do it this way, you need to realize T goes from 0 to 1. Think about it. If T is 0, this is P. Plug in T equals 0 here, you get 0, 0, 2, P. When T is 1, this becomes P plus Q minus P. The P's cancel, giving you Q. Yeah, if you plug in T equals 1 here, you get 4, 0, 0. So that's R1 of T. For R2 and R3, the other pieces, the other lines, be very similar. Change the 1 to a 2, change the P's to Q's, and change the Q to an R. This will be the parameterization for this bottom line here. Its formula is that. When T is 0, that's 4, 0, 0, Q. When T is 1, it's 0, 3, 0, R. Then for the last line, we're going from R back to P. When T is 0, here, gives you 0, 3, 0. When T is 1, you get 0, 0, 2, back to P. So for each one of these, T goes from 0 to 1, and that'll be your limits of integration for the line integrals. You're going to have to do 3 line integrals and add them together. What's the vector field? It's given to be y negative z y. Best way to type that in does include using curly braces so that you can plug in 3-dimensional points into this, or 3-dimensional vectors. Y negative z y. The first integral's integrand then will be, go back to doing circulation scalar line integrals. You take the dot product of f evaluated along the curve times the velocity vector for the curve. That'll be the first integrand function, 0. What's going on there? The vector field must be perpendicular to the tangent vectors. It must be perpendicular to this line, along that line. Is that easy to see? This axis is x-axis, this is y, this is z. Along this line, we are in the xz plane where y is 0. I will get 0, negative z, 0. And negative z, the second, okay, these vectors are going to all point to the right or left. That's what's going to happen. Because only the second component is non-zero in the y direction. They point to the left, actually, when z is positive. The vectors in the vector field are pointing this direction, and they are perpendicular to that line. That's why we got the dot product of 0. So the integral would be 0 as well. Along the other line, the second line, you would do this dot product. Fairly simple, but not 0. And along the third one, we do that. So the line integrals are going to be integrating 0, which of course is 0, but I'll write it anyway. Integrating negative 12t. Integrating 6. And adding the results, giving you a total of 0. The circulation is 0 around this curve, the total circulation. Not along each piece. It is the line integral along this curve is 0, but the line integral on this one and this one are not 0, but they cancel. This one must integrate to negative 6, and this one integrates to positive 6. So this is supposed to equal, again, the surface integral of the curl of f with respect to the surface and the outward pointing, the normal vector that's going towards you in this picture. Does Mathematica have a built-in curl? It does. How about that? How is it used? This kind of syntax looks like what we need. I think we can probably just do this. Curl of the vector field with respect to x, y, z. It's a constant vector. Being a constant vector and n being a constant vector, if this is going to integrate to 0 over this triangle, as it should according to Stokes' theorem, we're dotting it with n. Probably it's parallel to the triangle. It should be parallel to the triangle. Is that right? 2, 0, negative 1. That doesn't seem right. 2, 0, negative 1. Something is seeming wrong. Did it compute the curl correctly? Maybe we should compute the curl by hand. There's your m, there's your n, there's your p. Curl of f, again, should be py minus nz, comma, mz minus px, comma, nx minus my. Py is 1, nz is negative 1. Mz is 0, px is 0, nx is 0, my is 1. 2, 0, negative 1. Looks like Mathematica is correct. We want to compute this thing. That's a surface integral. You got to parameterize the surface and do the things you've been doing recently. If we want to use a rectangular parameterization involving u and v, we could focus on the bottom triangle. I mean, we're going to use the fact that this surface is the graph of z equals little f of xy equals 2 minus x over 2 minus 2y over 3. We can parameterize the bottom triangle. You did this on your assignment. The xy equation of that triangle is y equals 3 minus 3/4 x. Effectively, you can let x equal u, y equal v times 3 minus 3/4 u, right? You've done this kind of thing. U is going to go from 0 to 4, just like x goes from 0 to 4. V is a scaling parameter that, when you do it this way, always goes between 0 and 1. And then for the surface in 3 dimensions, we have to plug those things into little f. Z is f of u comma v 3 minus 3/4 u. You could expand this out if you like, but you don't have to. So then I look at the formula for f. 2 minus x over 2 minus 2/3 y. 2 minus x over 2 becomes u over 2 minus 2/3 y is 2/3 times this. Now simplify. Distribute this through the parentheses there. The 3's cancel first, you get 2 minus 2v, and then plus, it looks like, through some cancellation of the 3's and the 4 and the 2, plus 1/2 uv. Put these in a vector. By hand, you could call it r. In Mathematica, I better call it something different. Maybe I'll call it r surface, because it's parameterizing the surface. U comma v times 3 minus 3 u over 4, comma f of u comma v times 3 minus 3 u over 4. Did I define f? Doesn't look like it. Okay, define f first. Two minus x over 2 minus 2y over 3. So that's what that's the r function. We got to differentiate it with respect to u and v and take a cross product. There's the derivative with respect to u, which you can certainly do by hand, not too much of a problem. Differentiate with respect to v, maybe expand, and then take the cross product of those things. It's not a constant vector. Is it pointing towards you? Is it like this picture? You'd want the x, y, and z components of n to be positive, if that's the case. If u is between 0 and 4, are all these things positive? They could possibly be negative when u is as big as possible. If u is 4 here, 3 times 4 is 12. 12/8 is 3/2. You get 0. If u is 4 here, you get 2 minus 4 over 2 is 0. If u is 4 here, you get 3 minus 3 is 0. Yeah, you're just barely getting to 0 vector when u gets up to 4. But when u is less than 4, these are all positive. It is pointing towards you, like the picture. So finally, the appropriate double integral to do is to let v go from 0 to 1, u go from 0 to 4. F of this cross product dotted with the cross product itself. No, not f of the cross product, sorry. We do dot with the cross product, but we do not plug the cross product in there. We plug in the r surface into f. It should give 0. Oops, forgot. 19/3. Where's my mistake?
I believe you didn't use the curl.
I didn't use the curl. Oh yeah, that's the problem. Yep. I forgot it. I gotta take the curl of f. That's the vector field that gets integrated, not f itself. That was my mistake. Thanks. Can I do this? This seems like it could be trouble because of the u and the v. Can work? That's not going to work. I think I need to do x, y, and z first. Oh my. Maybe I don't. Okay, no, that doesn't make sense. X, Y, and Z, just a plain X, Y, and Z. It's constant. The curl is constant. It didn't have to be constant. If it were not constant, I could plug. Okay, I may as well give this a name. Pretend it's a function of X, Y, and Z, even though it's not. It's constant. In this case, it's a constant vector. But essentially, that is what I plug in the surface into. Ah. Thank you. There we go. 0. Oh, all that work to get 0. Is the integrand function 0? Must be, since the curl is a constant vector. But in general, you get an integrand function that's not necessarily always 0. But it is in this case.